Okay, time for a video. So I've done a short series recently on atmospheric phenomena, mostly around the jet stream, but also the polar vortex and some other stuff related to that, because I've been becoming increasingly alarmed at what I see happening in the Earth system. So because I recognize something alarming, and because I have this platform, I come on here and I talk about what's got me nervous or anxious in that domain. And why do I do that? Mental health. It's good to be able to talk these things through, organize my thoughts, get it off my chest, whatever you want to call it. However, turns out I'm not the only one. My wife got something in her mentions that pretty much reinforces what I've been saying for the last few weeks, and kind of even what I've been saying for the last year or so, which is that the Earth system has gone off the rails. Now, I can say that, and other people can say that, but I think we're doing a disservice to the community if we don't really explain what that means. Like, what are the rails? What's normal? Why is this abnormal? What are the impacts that are going to be a problem for us humans, and by extension, other forms of life? And also, if possible, where is all this taking us? Because I think it is taking us somewhere. I think that place is important to examine. And how we're going to get there is also important to examine. I say on this channel pretty regularly, fairly regularly, that I don't believe anything much more than one person in 1,000 is going to survive this. That's just my take. And I think that's a fairly supportable take. But for that to make sense, for that to resonate or to gain any traction, then I probably have to do some homework here. So I'm going to start a new series. I have another series called Massive Societal Change, which sort of addresses where civilization, society, I don't think civilization goes anywhere. I think civilization collapses, but where human organizing principles, societies, go as a result of global heating. And I did a whole series on that called Massive Societal Change. It's linked in the description. And I think I'm up to 14 videos in that series. I will have more as I think about impacts that are worth putting into the series. But this is a new series, somewhat related. I'm calling it for now out of the frying pan into the fire, because I think that's kind of what's coming. We're now headed into a very dark place, dark in terms of our prospects. I wrote a book. The link also in the description. The book is called It Was 100 Days, and that fits into the current series, the one I'm about to begin. And that book talks about the transition, maybe like video 2 in this series. I'm doing video 1, and there's probably 3. And video 2 is kind of what the book is about. And I'm already thinking about a second book that extends the first one, which would be like part 3 of this series. So this series is helping me work into the next book of the things I've published, and how I'm going to do that and what material I'm going to include. So I'm doing this, at least in part, to gear myself up for that next effort. So this kind of content doesn't do real well on YouTube because of the subject matter and because of me and how I present. So fair enough. If you want to boost this signal out there in algorithm land, then if you're not already, subscribe. That makes a big difference. And also, regardless, leave a like, because that sends a signal to YouTube that this kind of stuff needs some kind of distribution. And we'll see what happens there eventually. I'm getting close to 100 subscribers. Numbers don't mean much in this space, right? But it would be fun to cross 100. So if you haven't subscribed, it'd make me smile if we crossed 100. And of course, after that, I'm going to have to cross 1,000. So no slack. You're not getting any slack from me. So let's talk about what I'm going to talk about here. The first video, this one in the series, is going to describe the Earth system as it pertains and as it's relevant to global heating, humanity, why we're here, what we're doing, how we're able to do what we're doing, so that I can then go into the second video with that in the background to discuss, what's happening to us. Given where we are and how we got here, what's happening to us and what's the significance of that. And then the third video will be, again, extending that, where are we going? So we know where we are, then what are the drivers that are moving us out of our comfortable space that we're in now? What are the drivers moving us? And the third video will be, where are we going? And as I go through these, they become more speculative. All of this is a little bit speculative because we humans kind of don't really know a lot about the Earth dynamic system on the scale I'm talking about it here. But we know some things, and we have a lot of observations, and that's kind of key to this. The scientific method likes to collect a bunch of information, look at it for a long time, look at it collectively, right? Have a lot of people looking at it at the same time and hemming and hawing and trying to guess what it all means, and then making predictions or making models or coming up with explanations for what things are happening. And in this way, we, through observation and discussions of the observations, the data, we try to push back the frontiers of our knowing. We understand we don't know. We're not comfortable not knowing. And so we observe and we discuss, and then in that way we push back the frontiers. So that's all I'm doing here. That's all I'm doing. I'm just dealing with science. I'm not really dealing with politics. I'm not really dealing with human psychology, although that cannot be escaped. In my book, I don't deal with geopolitics. I do deal with human behavior quite a bit. In fact, the book is almost entirely about human behavior, because in the middle phase of this, human behavior really drives a lot of what we're going to be able to do, either to save ourselves or preserve something, bring things forward that we like, technology or knowledge or information or language or arts or whatever. Human behavior will determine how we behave in the face of a crisis, and to some extent, where we can go afterwards. That journey will depend on who's on the journey, who can get their shit wired up tight, fast enough, early enough that they can then be on that journey. So we'll see where this goes, right? As usual, I'm making this up as I present it. I have given some thought to it. I've written a book, so I'm a little bit ahead, but you're going to get it as I get it, as it comes to me. But actually, to start with, I want to mention this article that my wife came up with, and she read it to me. And I thought, oh, that's interesting, because this is pretty much in alignment with what I'm thinking. So this is from Damascus Byte. It's actually a website in the UK, damascusbyte.co.uk. And this came out today. I'm going to read this because it's actually pretty short. It's like 4 paragraphs, but they're all pretty good paragraphs, so we might as well read it all. And again, some of this is actually for video 2, but I want to include it now to give some credibility to why I have to talk about this topic right now, with urgency. I'm doing this now, okay? Meteorologists warn that an unusually early Arctic breakdown is forming in January with atmospheric signals not seen in decades. That's putting it mildly. Some of these atmospheric signals probably have not been seen in 15, maybe 20 million years. So, decades, eons, we can agree to disagree. So I will read this. That's dumb, but I'm going to do it anyway. It slipped quietly into specialist weather blogs a chart shared on X, a nervous comment from a TV forecaster who chose their words very carefully. An unusually early Arctic breakdown is forming in January, and the signals blinking in the upper atmosphere are something veterans say they haven't seen in decades. The maps look almost abstract, rings of color twisted out of shape above the North Pole, wind arrows bending where they shouldn't. Most of us are just looking at the gray sky outside the window, wondering if we'll need a scarf tomorrow. Yet, high above that quiet cloud deck, the polar atmosphere is behaving like a machine that's starting to rattle. Meteorologists are watching, arguing, refreshing model runs at 3 a.m. There is one question they can't shake: what an Arctic breakdown really looks like from the ground. So, they're nervous. I am, frankly, terrified. I'm really worried. This is bad, people. This is really bad. This article is going to talk about some shit that should make your hair stand up on end, but it won't, because no one understands this. There's so few of us who understand what's happening that you'd have to be pretty hardcore not to be frightened right now. Seriously hardcore. Picture a frozen dome of air thousands of kilometers wide, spinning like a top over the North Pole. On a normal January, that top stays tight and strong, locking the cold air in place. This year, it's wobbling early. A wobble in the summer in the Northern Hemisphere is not unexpected, but wobbling in essentially the dead of winter is very alarming. Meteorologists call this structure the polar vortex, and right now its core winds are weakening and tilting in ways that feel uncomfortably familiar to those who remember the brutal winters of the late 1980s and 1990s. So this can happen, but right now it's happening a lot. Like in the last few years, this has been happening frequently, almost constantly. And if you've been paying attention to the weather and the types of extreme weather we're getting, you may have begun to question what's going on. We tend to feel this not as some grand scientific event, but as, quote, weather that suddenly stops making sense. Yeah, exactly. A warm, wet spell in one country, snowstorms in another that shouldn't be there, temperature swings of 20 degrees C in a week in the same location. When the Arctic starts to lose its grip in January, cold air that was neatly stored over the pole can spill south in messy, unpredictable bursts. They'll call these Arctic blasts and things like that. What's been happening in the U.S. is way beyond this. I think they're going to focus mostly on the cold part, because the cold part is very dramatic. But we've actually been getting heat waves. And the heat waves, to some extent, are far more alarming. The hottest Christmas in record in many places in the U.S. this year. Well, not this year, of course, 2025. And what has been happening here in the U.S., and I assume elsewhere in the world, but like I say, I don't have a lot of visibility into that, is that we have record cold snaps that really do set records. And then those move off to be followed by record heat waves that really do set records. And then a week later, there'll be another cold snap that sets more and different records in the same kind of zip codes. And then followed by a few days later by another massive heat wave that sets even more heat records. And so this oscillation back and forth is symptomatic of a breakdown of the northern jet stream. Now, maybe they'll get into that in the article. I've done a lot of videos on this, okay, because I'm kind of losing my mind over this. This is bad. This is really bad. We have never really seen this. Yes, you can get a polar blast once in a while, and you will have a terrible winter or a terrible couple of weeks in the winter. What we're seeing now is not weather. This is a massive breakdown of the Earth dynamic system. This is a one-way journey, people. This is not weather anymore. Yes, you're going to get weather. Yes, of course. And the weatherman or weather woman will talk about the weather. But this is not weather. And you have to understand that. This is a breakdown of the Earth dynamic system. It is falling apart. This is terrifying. This is horrendous. In early January, a cluster of European and North American weather offices flagged the same thing, an unusual weakening wave climbing up into the atmosphere, nudging the polar vortex off-center. One UK forecaster posted a chart showing a 10 hectopascal wind speeds dropping sharply, adding just 3 words, "This is weird." And when you get scientists saying things like, "This is weird," then you need to step back, because we don't use language like that. We just don't. We might say, well, this is something to observe, or, well, we need to compare this to prior years. We need to do a study. We need to have more years of data. But when people in my position are finally saying, okay, I'm calling it, this is weird, then it's weird, okay? It is outside the boundaries. It is off the charts. It is off the map. And you'll say, well, that's just hyperbole. It always gets cold in the winter. No, I'm telling you something, and you need to understand this. We are off the map. This is bad. And I don't care what people think about the weather. And I don't care what people think about the cold. And I don't care that this happened in 1989. We are off the map now, people. And that's why I'm doing this video series. I need to explain to everyone here. We are off the map. This is weird. In the US, a research team compared current patterns with historical reanalysis data and found a similar configuration only a handful of times since the 1970s. The current configuration actually has been going on for a long time and has been repeating itself since about 2023. This is not too unusual for the last couple of years. This has been happening a lot. There's been a lot of chatter in the climate research space about this is not right. This doesn't look good. And if meteorologists are just now catching on to it, well, that doesn't surprise me. They're always late to the game. The climate research community has been looking at this since about 2023, and this is not right. In 1985 and 1991, comparable early season disruptions were followed by intense cold snaps in parts of Europe and North America. That doesn't guarantee a repeat this year, and the scientists are careful not to overpromise. We're getting massive cold snaps in the lower 48 United States. Record-breaking, followed by record-breaking heat, back to back to back to back, over and over for months now. The meteorologists are sandbagging this, or maybe this author of this article is sandbagging this. I'm telling you, this is unhinged. The system is coming apart, completely degrading and disintegrating. This is not good. This doesn't guarantee a repeat this year, and the scientists are careful not to overpromise. Still, the parallels are strong enough that some long-range models are leaning toward a burst of Arctic air bleeding south in late January or early February, even while others hold on to a milder pattern. The atmosphere looks like it's halfway through changing its mind. Yeah, good luck with that. Behind the drama is a set of physics that, in its own way, is beautifully simple. Physics usually is. By the way, some of this is recent knowledge. Yet we're still learning. But when you figure it out, the physics is generally pretty straightforward. We just don't know what it is at first. The polar vortex lives in the stratosphere, 15 to 20 kilometers above our heads, driven by the sharp contrast between sunlit tropics, the equator, and the sun-starved Arctic. The same also holds in the south, in the Antarctic, but it's a different situation. The similar physics. When waves from the lower atmosphere, pushed by mountain ranges, storm tracks, and unusual sea surface temperatures, the mechanisms actually are not that well known. When these waves punch upward, they can slow that circling wind, the polar vortex, and tilt or split the vortex. This Arctic breakdown doesn't instantly flip the weather. It loads the dice, increasing the chance that the following weeks, high-pressure systems will block usual storm paths and open gates for cold air to plunge south. Hopefully the article will mention it, but what really happens, the actual mechanism, is that the polar vortex has authority over the workings of the jet stream, the northern jet stream. When the polar vortex is off kilter or degraded, which it currently is, the northern polar jet stream falls apart. It is now, right now, completely fallen apart. See my last few videos on the northern polar jet stream. It is a mess. I've never seen anything like this. It can become a mess in summer, but we're in the dead of winter, and it is a mess in the dead of winter. And that's why I did a video some week and a half ago titled My Prediction for 2026 is that the summer is going to be crazy hot. How to read the warnings without losing your mind? Well, too late for me. I've already lost my mind. There's a simple habit that separates people who feel blindsided by extremes from those who feel at least somewhat prepared. They track patterns, not single headlines. When meteorologists talk about an early Arctic breakdown, which we're seeing, they're offering a pattern level alert. True. One particular move is to follow 3 things for your region over the next 2 to 3 weeks: temperature anomaly maps, jet stream positions, and ensemble forecasts, none of which the average person can do. I can do that. I do that actually just about every day now because I'm really worried what's going to happen. And I'm watching it, and I'm trying to study the patterns, and I'm trying to come up with a pattern of the patterns. I don't expect the average person to do that. That's why I'm on here. You don't need a degree to do this. Very true. Although it doesn't hurt. Many national weather services and serious hobbyists share these graphs daily. That's true. I've been kind of doing that. Look for those maps showing red and blue blobs relative to normal. That's your anomaly. If you see a tongue of deep blue sliding over your area repeatedly in the models, that's a hint. The jet stream, the fast river of air at cruising altitude, jet cruising, will often kink and dip more once the Arctic goes unstable. This is true. I just mentioned that. Those big loops on a map, that's where strange cold air or out-of-season warmth likes to drop. Let's be honest. Nobody checks ensemble forecasts every single day. Of course. That's fine. That's not a problem. That's just life. But when the experts start debating an Arctic breakdown, it's worth 5 minutes. Ensembles are just many slightly different versions of the future run by the same model. If most of them suddenly lean toward a colder pattern after a week or two, that's a stronger signal that a single dramatic run shared on. Okay, so they're saying, yeah, check your weather conditions, figure out what's happening, pay attention. Do you really have to? I mean, what do you get out of this if you're paying attention? I can show you a picture of the jet stream. I think it's probably, yeah. This is the jet stream right now, folks. Does that mean anything to you? I can show you the polar vortex. This is live data right now. This is at, again, earth.nullschool.net, and you end up here, or you have to click through to here or something. Let's look at the polar vortex. Yep, it's messed up. It should be centered over the North Pole. It's centered over, what is that? Svalbard, off of Norway. Earlier, it was centered over Greenland. It's moving around. There are 2 loops at least, both of which are pretty strong right now. One of them is situated over Alaska, one of them over Svalbard. And this is bad. This is bad news. And what that does to us is it gives us this jet stream, and this is absolute chaos. Complete chaos. This has no authority. This jet stream isn't controlling anything. It's not controlling Arctic air masses coming south. It's not controlling hot air masses going north. It's looping, it's bending, it's breaking off, it's forming cold core cyclones. This is nuts. And this is the dead of winter. It should be as well formed. Let me pull up the south. Remember, this is a globe. We'll pull up the south. Here's the South Pole. This is pretty well formed. It's got some kinks in it, but it's their summer. So it's not too surprising that it's got some malformations in it. It's their summer. But that's what the one in the north should look like. The one in the north should look more like this. But instead, the one in the north looks more like a summer pattern. And this is off the map. This is really off the charts. No one really knows what this means for the future. They know it's going to be bad. I'm really worried for this summer. I really am. Because this is going to get worse come summertime. This already looks like a summertime pattern. This is going to get worse. So this is not really what I wanted to talk about today. So I'm going to get back on the topic of where are we? Video 1 is supposed to be describing the Earth system. So I will now do that with much hand waving. You can look all this stuff up. A lot of it is probably things you've already heard, and but it's necessary to set the context for the discussions that follow. So here we go. Basic things. Don't be offended. I just have to say obvious things. The Earth is a globe. We were just looking at it. The Earth is a globe. It is a sphere. It has a North Pole and a South Pole. They alternate in the seasons. When the North Pole is in the summertime, then the South Pole is in the winter, and vice versa. The equator doesn't have seasons. The equatorial region, which is the biggest place, by the way, of the Earth, doesn't have seasons. Maybe it has a dry season and a wet season, and that's about it. A monsoon season or something like that, and that's about it. Most of the land of this planet is actually in the northern hemisphere, not at the equator. There's a fair amount of land at the equator, most of northern Africa and a good part of South America. But by and large, the land masses are in the north. And there's almost nothing in the south. There's Australia and the tip of Africa and the tip of South America. That's how things are distributed. The largest body of water, there are 7 seas. I couldn't tell you what they are, but the largest body of water is the Pacific Ocean. The Pacific Ocean and what's happening there tends to drive the entire system. There's another body of water that's fairly large, which is the Atlantic Ocean. The Atlantic Ocean doesn't have quite as much influence on the global system, but it does have a lot of influence on Europe. And I'll discuss that in a minute, if I remember. The Atlantic is important to what's happening in Europe. The planet, as I just described it, that's the static description. There's water, there's land, which is above water. There's an atmosphere. There's a biosphere. That's us, plants and animals. That's a static description. But the Earth is not static. It is dynamic. It's moving. When I was showing you this picture, this is dynamics. The colored bars are wind speed and direction, and the eddies and the flows and the kinks and the bends. All that stuff changes, and it changes daily, and it changes with the seasons. There's also a ocean, and I can bring up the ocean, and I can bring up the sea surface temperatures. This is the sea surface temperatures of the oceans. And you can see here the U.S., and this is the Atlantic Ocean. The orange and yellow are warmer, anomalously warm. So it's warmer than it should be by historical measures. And the blue, as you see over here in the Pacific, is anomalously cool. These are sea surface temperature anomalies. The actual temperatures are also available, and these are the actual temperatures. So again, the dark red is hot. And here's some purple over here. That's 88 degrees Fahrenheit. I could do Celsius for you Europeans, but right now it's set to Fahrenheit. Over here in the Arabian Sea, it's 83 degrees Fahrenheit. And down here around Antarctica in the blue, the temperature is 32 degrees Fahrenheit. That's freezing. And up here in the north, because of course it's the north, well, for one thing, there's a lot of ice, so that's 28.8, and these blue waters down here are 32.9, so just at freezing. And something like the Mediterranean Ocean is actually a little bit anomalously hot. So they see surface temperatures, but it is anomalously hot. This is different. So this is showing that it is 1.5 degrees C hotter than it should be. And the sea surface temperatures vary. Not only is the system dynamic in the parts that are moving, but it's dynamic in that one part can be warmer than another part, and one other part can be cooler than it normally is. So the system is constantly changing, constantly moving. And when climate scientists say something like, wow, we're having some weird cold air masses coming out of the north, then of course the detractors will say, well, it's always cold in the winter. And it's like, guys, yes, we expect it to be cold in the winter. But there are things happening in the Earth system that are not correct, not expected, that are operating outside of expectations. To the normal Joe Blow, that doesn't matter. They don't care. But to scientists, it matters a lot. There is more to this than even what's changing and what scientists think about it. This system, and I'm looking at ocean temperatures now, where it's warm at the equator and it tends to be cooler at the poles, okay, and then there's a gradient in between. This system is a contingent fact of history. The planet didn't used to be like this. Hot at the equator and colder at the poles. It's only been this way because for the last 5 million years, maybe even 10 million years if you allow for a cooling period, we have been in an ice age. And remnants of the ice age still remain. Down here, if you go down here to Antarctica, of course I'm looking at sea surface temperature, so that doesn't matter. Let's go to the air and let's do temperature, okay? Down here in the Arctic, the surface, here we go. The temperatures of the Antarctic is determined by the fact that it's covered with ice. This Antarctic continent, is covered with ice. You can't really see that here. I'd have to go to a different view. But it's really cold down here. And this ice is left over from the ice age, from the last glacial maximum. Before we entered an ice age 5 million years ago, there was no ice on Antarctica. In fact, there were forests on Antarctica. And there were life forms that you would not associate it with what it is now. It's covered with ice. You see penguins and seals, right? There were life forms down there. There were amphibians, reptiles, and I guess even dinosaurs, depending on who you want to believe. If you go to Antarctica, you can find fossilized forests, the stumps of the dead trees that are now turned into fossils because it has been, 10 million years. So that's what happens. Wood gets fossilized. It's called, petrified wood. And so we have evidence that it was not always like this. The way it is now is a contingent fact of history. 5 million years of history of being in an ice age. We are living on a planet that remembers being covered in ice. Humans have been here for 300,000 years. Our entire Homo sapiens, our entire evolutionary history, including our culture, our discoveries about the earth, our discoveries about ourselves, our discoveries of fire and domesticating animals and domesticating plants, all that entire history, written and unwritten, happened during glacial times when the ice was approaching and retreating and approaching and retreating. The ice, again, I'm just dealing with what's now. The ice expansion and retreat is driven by something called the Milankovitch cycles. The Milankovitch cycles weren't even known. It was a mystery. Why did the ice advance and why did it retreat and why did it seem to do this on a periodic basis? The mechanism behind that wasn't even known. We knew it was doing that, but we had no idea why until the age of computers came along, because we could finally do data analysis and we discovered that it was being driven by orbital mechanics. The Earth is not only a sphere, it orbits the sun, and it also orbits in a complex way, in a three-body problem way. It also orbits the other planets. It slightly orbits Mars, it slightly orbits Venus. The Earth and the Moon system go around each other. They orbit a point somewhere in the middle. It's actually below the surface of the Earth, but it doesn't matter. It's between the center of the Earth and the center of the Moon. There's another center, a third center, that they both orbit around. And the tilt of the Earth and its angle in the solar system plane of ecliptic, where it is relative to the sun, closer or further away, all these parts of Earth dynamics are like a clock, like gears in a clock. And depending on how those gears align and how they mesh and what's happening with the Earth, then we can have periods of time, and they're fairly long periods of time, when the Earth is going to tend to be colder than other long periods of time when the Earth will tend to be warmer. Now, back in history, when there was a lot of CO2 in the atmosphere, 2,000 parts per million or so, it didn't really matter what the Milankovitch cycles were doing. They were there because they're orbital mechanics. the Earth's orbit would happen whether we were here or not. It would happen whether there was water or not on the planet. It would happen whether the planet had an atmosphere or not. The orbital mechanics are the rock. The rock itself, going around the sun, orbiting around the moon, or being interfered with by the planets, including Jupiter and even Saturn. The orbital mechanics of the Earth are just physics of the Earth as a rock. And what determines whether we ever have ice ages or not is something else, and that's the atmosphere. If the atmosphere has a lot of CO2, CO2 is a greenhouse gas, meaning it heats the Earth. The current temperature of the Earth is about 70 degrees Fahrenheit warmer than it would be without the greenhouse effect. So that's a good thing. A place like Mars, which has a very thin, almost non-existent atmosphere, doesn't have a greenhouse effect, and therefore it's freezing all the time. Another planet like Venus has a very out-of-control greenhouse effect, and the surface of Venus is hot enough to melt lead. Same solar system, same sun, same sunspots, same everything, but Venus, because of its atmosphere, is hot enough to melt lead. Earth also has an atmosphere, but it's not so thick and dense that it gets really hot. It does get hot because we have some CO2 in our atmosphere, and the atmosphere is important. So because there was a lot of CO2 in the atmosphere, the earlier impacts of the Milankovitch cycles didn't matter. Maybe the Earth got a little warmer, a little colder, but you wouldn't have noticed, and there were alligators at the poles. Because even though maybe it could cool a little bit and warm a little bit, it never changed enough that reptiles couldn't survive in Antarctica, and they did. Then plants were constantly drawing down the CO2 in the atmosphere and burying it. Weathering of mountain ranges, including big mountain range building events like the building of the Himalayan mountains. We go through periods of enormously important weathering of mountains, and the weathering tends to pull CO2 out of the atmosphere as well. These events, plants drawing down CO2 and burying it, it's called sequestration, and mountains weathering and absorbing CO2 and leaving it in the oceans. These processes happen over geologic time. But over geologic time, enough CO2 was drawn out of the atmosphere that the greenhouse effect began to be decreased, and the planet began to cool. And then suddenly, we went into a Milankovitch cycle that would also want to cool the planet, and because of the combination of enough CO2 having been pulled out of the atmosphere to cool the atmosphere a little bit, and then the orbital mechanics coming along and cooling the atmosphere a little bit, we dropped into an ice age, and that was about 5 million years ago. We have been in an ice age ever since. Ice ages tend to be reinforcing. The ice itself creates more ice. It does this by creating a lot of cold. It does this by being very reflective. The sunlight coming in hits the ice and reflects back to space. It's harder for the sun to warm the planet when the planet has a lot of ice on it. In fact, there have been times in the Earth's past when the atmosphere wasn't configured the way it is now, when this planet was mostly covered with ice, almost entirely covered with ice. Maybe at the very equator, there was a small band of exposed water and land from the heat of the sun. They call it snowball Earth. How do we get out of snowball Earth? Because volcanic activity is a constant, and volcanoes were lofting CO2 into the atmosphere all the time, and methane as well, another greenhouse gas. But because the Earth was covered with ice, there was no weathering. And because the Earth had no life on it, there was no carbon sequestration. So the carbon accumulated. And then when the Milankovitch cycles changed or something else changed, then the Earth was able to thaw from the accumulation of CO2 in the atmosphere, the greenhouse effect. And we've been snowball Earth, I want to say twice, but it's probably worth looking up if you care about that kind of thing. But since things have changed enough and there's a lot of life on this planet and the carbon cycle is really robust, we haven't had snowball Earth again. And until recently, we did go into an ice age. And that was about 5 million years ago. Well, guess what? Humans have been busy digging up fossil fuels and setting them on fire. That's reversing the process of carbon sequestration and instead pumping carbon into the atmosphere again. This is pushing us back into another phase of the Earth, which is the hothouse Earth. And under the hothouse Earth, which the Earth has mostly been since the origin of life, we have mostly been a hothouse at various times, then we're going to be that again. We're heading back for that. We're at during the other interglacial or glacial events, the amount of CO2 in the atmosphere could be as low as 150 parts per million, maybe as much as 200, depending on what's happening with like volcanoes and thawing events and things like that, and weathering and stuff like that. But right now, because we've been pulling fossil fuels out of the ground and reversing the process, setting fire to it, putting the CO2 back in the atmosphere, because we've been doing that, the amount of CO2 in the atmosphere has now climbed from what historically for the last 5 million years is maybe between 150 and 200 parts per million to about 430 parts per million currently, and going up rapidly because we're doing what we're doing rapidly, and we're not stopping, and we're not going to stop. So geologists have said, okay, because we've done what we did, we have now terminated the Ice Age. The Ice Age began 5 million years ago, and it ended with us. This very generation. We ended the Ice Age, probably. Now, it's important to know all this because everything that you know about humanity on this planet, the written history, the art, the civilizations, the trade routes, all the innovations, all the inventions, the gunpowder, the paper, right, the steam engine, everything that you know, that we all know and accept, and we learned this in 3rd grade, right, 5th grade. We learn all this stuff, and we learn what humans did. Everything we knew happened during a very short period of time between glacial events during the Ice Age. We have terminated the Ice Age. It's over. It's done. Will the Earth ever go into another Ice Age? Yeah, it could. But it won't happen except over geologic time. So that's millions of years, tens of millions of years. We have terminated the Ice Age that is 5 million years up to now, and we're not going back. This planet will not go back. And that's just how it is. That's not a bad thing. In the 70s, I remember in the 70s, about the time they had discovered the Milankovitch effect. So they knew that there was a pendulum swing. There's more ice, there's less ice. There's more ice, there's less ice. And when it came time to discuss their findings with the common people, right, the mass media, they said, oh yes, Earth will go into another glacial event. We don't want to call it an Ice Age. People call it an Ice Age. There's one Ice Age. It's 5 million years long, and there's glacial events, okay? More ice, less ice, more ice, less ice. We'll be going into another glacial maximum at some point in the future. That's what they said. And they were basing that on the Milankovitch cycles, which they had just discovered. And they suddenly understood what was making this pendulum swing of there's a lot of ice, now there's less ice. Oh, now there's a lot of ice. Oh, and suddenly there's less ice. Over, again, hundreds of thousands of years, millions of years, these cycles would repeat themselves. And they discovered the Milankovitch cycles. And they did that using high-speed computers and mathematical models, and they figured out what was happening. And then they said, and because this is now physics, and because we understand it, we can say there will be another glacial maximum. That this interglacial, where there's minimum ice, will be reversed. And we'll go back into a cold period with lots more ice. That's what they said in the 70s. There was a completely different process taking place. That the geologists, who were the ones who study the glaciers and the glacial maxima and minima and the 5 million year long Ice Age, these geologists didn't even know about. A whole parallel process that the geologists had no idea was happening, even though it's in their wheelhouse. They just didn't have any idea what was happening because nobody did. And that was, we were enhancing the greenhouse effect. The oil companies knew. They weren't talking. The geologists did not know because they were studying the Milankovitch effect cycles. We have been pumping CO2 into the atmosphere. So even though we could, according to the Milankovitch cycles, which is just orbital mechanics, right? That happens whether we're here or not. We could go into another glacial maximum, but we won't because now we can't. Because we have taken the Earth back to conditions that existed before the Ice Age. We have terminated the Ice Age. at 430 parts per million of CO2 in the atmosphere. That's enough greenhouse effect to terminate the ice age. And it has now officially been called. They called it, I don't know, 10 years ago. Yep, we're now in a termination situation. Terminated the ice age. Where do you go after you terminate the ice age? Well, without ice, you're going to go into a hotter period. And climatologists now come in and they say, interesting. The planet has also had hot periods. We know that. We can see that in the sediment records. We can see that in the fossil record. We have plenty of evidence to suggest that the Earth was hotter. And the climate change detractors will say, oh, yes, of course, it was hotter in the past. Well, that's no big deal then. We're going to be hotter now. It's no big deal. Fine, you can take that approach if you want to. But remember, the 300,000 years of human history, of human development, and the 8,000 years of recorded history all happened during an ice age. So what is hothouse Earth going to do to us? Well, that's the other couple of videos in this series. I will be talking about that as best I can. Talk about that because some of it is unknown, but not all of it by any means. So that's kind of the picture of where we are. We are on a planet that is mostly water on the surface and a fair amount of soil. We have been in an ice age that lasts about 5 million years, in which the CO2 in the atmosphere, which is a greenhouse gas, varied between about 150 parts per million to about 200, maybe 250 parts per million. Now it's at 430, and it's going up like a moonshot. So we've terminated the ice age. We are going into a different place. Now the Earth is a machine. The Earth is a machine. And this machine is what's called a heat engine. And when I'm looking at the planet here, I want you to notice these are, let's see, what have I got here? This is air surface temperature. Okay, so this is surface temperatures. And it's a little warmer at the poles. What temperature? Yes, this is the right thing. It's a little warmer at the equator. I'm sorry. I've got 26 degrees C at the equator. And up here in Saudi Arabia, it's about 7 degrees C. And up here in Europe, like maybe Germany, it's 1 degree C. And over here in Russia, where it's purple, it's minus 44 degrees C. So it's colder in the north up here, and it's warmer at the equator. Now, that's interesting because the gradient between the hot region and the cold region can do work. This is kind of how your internal combustion engine works. The internal combustion engine, which is also a heat engine, it works on a cycle of heat. It pulls in cold air and fuel. It ignites the fuel and heats the air. The air then expands and does work against the piston. And then it pushes the hot gases out, pulls in new cold air with new fuel, and ignites that. And so your internal combustion engine works as a heat engine. It takes cold air and it heats it, and it uses the expansion of that heated air, combustion, to do work. Your internal combustion engine, if it's running on gasoline or diesel, or, well, yeah, I guess those are your two choices, natural gas, is a heat engine. Another heat engine is something like a steam engine. Well, that's external combustion, but the steam pistons in a steam engine, like a railway engine or something like that, it's working in the same principle. It has a cold cycle and a hot cycle, and a cold cycle and a hot cycle, and that makes the wheels turn. You can harness that energy. Another heat engine is a power plant that's burning fossil fuels like coal, crude oil, which they do burn, and natural gas. So in that case, the expansion of the hot fuel, coal and natural gas probably, is used to expand air quickly. And that expanded air is forced over a turbine. And the turbine is attached to a generator. So we bring, again, it's the same story. We bring in cold air on one end, feed it with fuel, set the fuel on fire, let the air expand, and feed the expanding air over a turbine to turn the turbine. It's a heat engine. The Earth is a heat engine. The heat engine of the Earth manifests itself in cyclones, hurricanes, typhoons, and cyclones, as they're called in the south of the equator. Hurricanes spin because a hurricane or a typhoon is a heat engine. The spinning comes from heat. And heat, in the case of a tropical cyclone or a hurricane or a typhoon, the heat comes from water. So when we're showing the temperatures of the water here, the fact that there is heat down here in these places, and there's this may not be. Is this actually the best view? Okay, there is ocean. Okay, there is ocean, and I can do sea surface temperatures. Since we're talking about hurricanes, we'll look at the ocean surface itself. Right. Okay, so here is the oceans where a lot of the heat on the Earth actually resides. There isn't much heat on the Earth on land because land doesn't have the ability to store heat very well. Water, on the other hand, has a very high specific heat. Air also doesn't store heat very well. It's necessary to move heat around, and the heat engine of Earth operates almost exactly the same way that a heat engine, like an internal combustion engine or a power plant, operates. Cold air is replaced by hot air, and that makes things move. So here we are in the water. You'll see there's a lot of heat in places like, well, this is the South Pacific, and we can go to the here's the South Atlantic, right? This is off of Africa down here, and this is off of Saudi Arabia and off of India. The water temperature is like 85 degrees Fahrenheit, so this is pretty hot. This is pretty hot water down here. 85 degrees. These are. Oh, here's a. See this little. Let me get my drawing tool. Okay, you see this right here? That's a cyclone because it's south of the equator and it's spinning. It's a cyclone by definition. So we have a cyclone right there operating, and it is over hot water, and that's how it works. The cyclone is spinning because of the hot water. Australia, they've been having cyclones. They just had one recently come ashore. I don't see anything right now heading for Australia, but there is hot water. This purple water is 88 degrees, almost 90 degrees. This is 87. So this is all primed for generating cyclones. Cyclones over water are heat engines, and the planet as a whole is a heat engine. And all the prevailing winds, everything we thought we knew about the weather, the westerlies, the trade winds, the doldrums, the horse latitudes, right? Everything we thought we knew about the winds, which is we learned mostly from sailing, right? The sailing ships needed to know about the winds. So they knew all about the winds. The trade winds are called the trade winds because that's how you got to where you wanted to trade your goods. So the prevailing winds are all there because the Earth is a heat engine. The Earth is a heat engine. And all this movement of all this air is because there is a temperature differential between the equator and the pole. That's what's driving all this. It's a heat engine. And the differences are created by the sun shining mostly on the equator because that's how it works. The equator is always pointing towards the sun to some degree, and a lot of the sunlight falls on the equator. Very little sunlight falls on the poles, especially when they are covered with ice, which has historically been the case because we've been in an ice age. So with all that reflective ice, it's hard for the sun to heat the poles. So we have a differential in temperature, and that drives the heat engine of the Earth, and that gives you your weather, because the winds give you your weather. And the problem with this is the following. If I go back to the atmosphere and I change from, instead of surface, I go to the top of the atmosphere. This is now in the stratosphere. This is where the atmosphere meets space, and it looks very different than on the surface. This is the same view at the surface, and you see there are definitely winds on the surface, but when you get up high up in the stratosphere, the winds are crazy winds, hundreds of miles an hour. These in turn drive winds a little further down called the jet stream. We discovered the jet stream before we discovered the polar vortex. We didn't know where the jet stream really came from, and then we discovered the polar vortex. And then we learned, again, later, that changes in the polar vortex affect the jet stream. That wasn't expected. Why would the polar vortex change? Because of a phenomenon called sudden stratospheric warming, which is what we are experiencing now in the polar vortex. I will go back to the stratosphere, and I will tilt this to look at the North Pole. And this is the current polar vortex. This is current conditions. There's two. And neither one is centered over the North Pole. So things are wonky. This is not good. This is causing massive disturbances in the jet stream, which I've spoken of several times now on this channel. And this is the resulting jet stream, and it is a mess. This is not giving you your normal weather. The heat engine of the Earth, that gives you your weather, that influences your seasons, that gives you ice at the poles, the heat engine of the Earth has broken. It's falling apart. The wheels are coming off. And when climate scientists, and increasingly, although still rarely, meteorologists are looking at the weather, and then they see this going on, they're beginning to realize that the weather, the things that people look at on a daily basis, is being driven not by prevailing winds and the cold fronts and heat fronts. It's being driven by a breakdown of the Earth system. The Earth dynamic system, the heat engine of the planet. As we have known that for our entire evolved history on this planet, 300,000 years, as we have recorded that history for 8,000 years, and as life on this planet has been evolving for 5 million years during the current ice age, now terminated, that is all going out the window. The heat engine of the Earth, as it operated for 5 million years, is changing. That's a time to worry. Now, I've been talking in this video about how the Earth is, how it's set up. What is the Earth? It is a heat engine. Why is it a heat engine? Because there's differential changes in temperature from the poles to the equator. All of this is driving the wind. The wind drives all your weather. The Earth, the heat engine of the Earth, moves heat from the equator to the poles where it can do work, melt ice, disappear into the space, whatever else is it going to do. And the prevailing winds, as we have known these, and we've been able to name them, the jet stream, right? The trade winds, the westerlies, and all the high pressures and all the low pressures and the Rossby waves and the Hadley cells, all these things that science has discovered, all these things that affect people's daily lives with the weather and the seasons and then the seasons and the weather, all these things have come to the front of our knowledge through science. We now understand what the Earth is. It is a heat engine. And the heat on the planet is there because of a combination of the sun, which doesn't change, and the atmospheric chemistry, which does. We have been increasing the greenhouse effect and heating the planet. And the heat does not stay at the equator. The heating is happening everywhere. And the sudden stratospheric warming that we're observing affecting the polar vortex is happening because of global heating. That's what's happening. We did that. The disruption to the polar vortex, this, which is bad, we did that. I can't believe that. That can't be true. It must be weather warfare. It must be HAARP. It must be sunspots. It must be God's will. We can't possibly do that. Yeah, well, sorry, Sparky, we did that. We did this, and it's not going away. I mean, it may go away, but it'll come back because global heating is a thing. And 430 parts per million of CO2 gave us this. There you go. Is it a good thing? Is it a bad thing? Well, we've terminated the ice age, 5 million years of glacial epochs, and that's gone. We don't have to worry about that happening. And then, but then we get this. That's your polar jet stream. That's supposed to be protecting you from cold Arctic air. That's not doing it. That is not fit for purpose. This isn't keeping the Arctic air at the North Pole. And when I read that article, and people are saying, "Uh-oh, oops, whoopsie, Oopsie doopsie. We kind of fucked up. Yeah, that's what they're saying. This is bad, people. There's no good news here. There's no good news here. This should be a ring of high-speed winds focused, centered on the North Pole. And it is none of those things. It's not even hardly remarkable. There's almost nothing here to point to and say, oh yeah, that's the jet stream. This, you're calling this the jet stream? I don't think so. This is a mess. So this video is about how the system works, where we are now, and what are going to be the implications for the future. The next video is going to be about basically what's happening. Why are we worried? Why are we worried? Why is anybody worried about any of this? So it's all kinky and bendy, and so what? It's the jet stream. It has a name, so that's a good thing. And who cares? I mean, it's just kinky and bendy, and it's not a circle, it's not a ring, but who cares if it's a ring or a circle? And, well, okay, it's not holding back the Arctic air. Oh, well, that is a little bit of a problem. But so what? We'll get through it. It's winter. It's going to be cold. We'll just put on extra layers, and, hopefully the electric grid doesn't go down, and the fuels are still available to run our cars and run our heaters and run our industrial processes, and we'll be fine. We'll get through it. It's like, yeah, but this is your planet. This is the machine in which you live. This is the heat engine that you live inside of. And it's on the move. It's going someplace, people. And I wish I could describe to you how terrifying that is. We've been here for a long time. We've been taking advantage of whatever it is that was amenable to our survival. We built civilizations, many of them, some of which have come and gone already. We made discoveries. We invented technologies. We had a Bronze Age. We had an Iron Age. We had an industrial era. And then we, using metallurgy and material science and science in general, right? Doing all the things we do with metals and materials and refining and mixing things. And we invented solar panels, and we invented nuclear energy, and then of course, all the silicon chips that go into all your computers. That's all what we did. We did all that inside of this heat engine because it was predictable and it was amenable to our behaviors, and because there was an area where the temperatures, and because there was an area that wasn't frozen all the time, right? Here it is near the equator. There's a part of the United States, there's a part of South America that isn't frozen. Yes, in the far north and the far south, but there's a part that isn't. North Africa, it's pleasant temperatures there. And because the Earth system was able to dispose of the heat that was available at 250 parts per million of CO2, because the Earth system could dispose of that heat, we had the growing and living and civilization zones that we had. Because there was no advancing of the ice fronts of the glaciers, we didn't have a drop in sea level rise. Because there was so much ice locked up on Greenland and Antarctica, we didn't have an increase in sea level rise. Everything has been the way it's been because of the Earth being the way it is. And now that's changing. How is it going to change? What parts of it are changing first? Well, that's going to be the subject for the next two videos. And of course, the real question is going to be, so what does all this mean for us? Yeah, that's the good question, isn't it? Yeah, the Earth as it's been configured and the heat engine as it's been operating has allowed us to do everything that we've been doing. Will we still be able to do the things we do, where we do them, and how we do them after the Earth has changed? Because that's what it's going to do. And the direction it's heading is not another ice age. And the direction it's heading is hot-house Earth. It's going to get hot. And we can still debate how hot it will get, and we don't have a lot of data. We're not really certain about predicting how hot it could be. We're not really willing to go out on a limb. And, let's face it, it's alarmist. You'll lose your job. You'll get fired. What is wrong with my camera? Let me see if I can fix this camera. See, it doesn't know how to focus. You have to kind of do this. There. Okay. Now it's focused. We can't assume that the places where we grow crops today during an interglacial will be the same place we can grow crops 5, 10, 20 years from now. The places where you have cities now, a lot of them coastal, a lot of them in temperate regions, like the middle of Europe, the middle of North America, temperate parts of Africa, most of the parts of Asia. We can't assume that once the Earth has gone on this excursion and taken us into a hothouse scenario, that any of these places will make sense anymore. And as I'm considering my second book in the series, after I did It Was 100 Days, if I consider the second book, the follow-on book, I have to consider, at least in my thoughts, where could we be headed? And as I think about it, and as I sit here and watch this system basically breaking down, and this is nuts. As I'm watching this system break down and contemplate where all this is going to take us, what's it going to be like when there's no cold at the North Pole? What's it going to be like when the jet stream is completely shut down and it can't hold cold air at the North Pole, and it can't keep warm air from going north from the equator? What's going to happen when the jet streams are gone? What's going to happen when the prevailing winds are gone? What's going to happen as the Earth becomes increasingly the same temperature from pole to pole? What's that going to mean for us? What about continental interiors? We actually expect them to become deserts. Without the prevailing winds to blow storms across the continents in a regular way, then they just don't have rain, and the continental interiors become deserts. What's that going to mean to people in interior Europe, interior Asia, interior Africa, and of course interior North America, Canada and the US, and of course most of South America? What's it going to mean for them if their continental interiors dry up because we've blown up the heat engine? Because the heat engine is moving air, and the air is moving moisture, and the moisture moves clouds, and the clouds rain here and there. And sometimes you get rain, and sometimes you get snow, depending on the season. But if you don't have seasons, you only get rain. And if you're not getting snow, you're not storing snow in the mountains, well, then what are you going to drink in the summer? And it just rains, and it rains torrents, and the rains run off, and it runs off to the sea, and you have no rain, no water left behind, and maybe you have some reservoirs, but maybe the reservoirs can't even hold back the torrential rains that you're getting. And then it all dries up, because you're in the continental interior and the winds have stopped. And we're on our journey now, folks. And I really have to stop and think about where we're likely to go. I've mentioned a few things here. The next video in this series will be, okay, what is happening to us? I'll have to come back to this picture again and talk about all the impacts on the Earth system, the heat engine of the Earth system. And I wasn't even on the right screen. I meant to be there. This picture is going to be part of what is happening to us, and we're going to have to look at this and consider what is going to happen to the rest of the planet when these systems, this heat engine and these systems have shut down or disappeared. And that's a tough discussion, folks. That's a rough discussion, and I don't think you're going to get any clues, to be honest. I'm going to do my best. I'm going to do my best to look at this and see if this can be figured out. But honestly, it doesn't look good. There's nothing we can do. We can't stop this. There's nowhere we can go. It's going to be really hard to predict it, what's going to happen, and where you're supposed to be to avoid this. And as for when, we're in it. We're in it now. That's supposed to be the jet stream. That's today's data. And, don't even get me started on the polar vortex. This is today's data. What are we going to, you can't do anything about this. And the only thing we could possibly do is we could say, okay, we're going to stop burning fossil fuels. We're going to stop making the situation worse. Well, you can't do that either. You can't do that either. Now, that's a topic for the second video. What is happening to us? Is there anything we can do? The answer is no. There's nothing you can do. Preview of coming attractions, I guess. So that's what I got. Thank you for dropping by. Let me look at the chat. Divine Hazel came. Hi, Hazel. Yeah, I be okay today. I'm a little stressed out. I'm really stressed out. And I don't know. We'll see. I guess we'll see. Next video in the series will be about what is happening to us. That's also pretty well understood. And then the third video in the series will be, and where do we go after this? And yeah, not good. Not looking good, folks. Anyway, if you want to watch all the videos, my usual advice is between now and then, don't die.